Hello everyone, my name is Ethan Harris, and today we are going to be discussing the unit circle. So what is the unit circle? Well, the unit circle is a way to represent the cosine and the sine and all of their real numbers given pretty much any angle, be it in terms of degrees or in terms of radians. It's used as a tool to better remember and visualize values of cosine and sine, typically seen with common angles with degrees and radians that you'll run into. So like 45 degrees, 30, 60, 120, and so on. So how do we make the unit circle? So we're going to go over the construction of the unit circle. So first we have to begin with the general equation of circles. So if we look at the general equation here, we see that we have x minus h to the second power plus y minus k to the second power equals to r to the second power. However, when we're looking at the unit circle, we only really care about it in simple terms. The unit circle is going to be centered at the origin, so 0, 0, and the radius of the unit circle is actually going to just be 1. So the equation of the circle simplifies down to simply x squared plus y squared equals 1. Now the radius and triangles. So the way that we do this here is that we sketch a line from the origin to a point on the circle there. And between the line and the x-axis, this creates an angle theta. And we can observe that the cosine and sine at theta would equal the xy components where the radius touches the point of the circle. Or in other words, we can make the observation that x squared plus y squared equals 1. We can actually insert cosine and sine in the place of x and y there, because cosine squared plus sine squared is equal to 1. And that's what you're seeing here on the right, is that the hypotenuse of this triangle that's made out of cosine and sine here, that hypotenuse is of length 1. And we can see that the x and y components of this triangle actually line up with where the hypotenuse touches the outer edge of the circle, and therefore we can deduce that the x and y components of this point on the circle is equivalent to cosine and sine at the given angle. And so to kind of show this, we're going to walk through a few of the common thetas and points that you can find on the unit circle. And the first most obvious ones are where the unit circle intersects with the x and y axis. And as you can see here with my sketches, I have a before and after here, and you can see that there are intersections at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And if you were to evaluate these points in terms of like angles, so say angle 0 or 2 pi here on the right side touching the x-axis, if you were to input cosine of 0 or cosine of 2 pi, you would find that the resulting value is 1, thus matching this component here. Meanwhile, if you were to input sine of 2 pi or 0 degrees or 360 degrees, you would see that the result is also 0 in this case, matching the y component of this point on the unit circle. And if you were to do this for any other point, you would see the same thing. And we will actually see this as we observe 45-degree angles. Now, when I say 45-degree angles, I'm more saying that we begin with the 45-degree angle and then we take a 90-degree increase. So you'll see that it'll go from 45 to 135. And the reason that we do this is because these will actually end up having very similar values, and they will only differ in terms of their position in regards to the origin. So what do I mean by this? Well, if we look at this spot here, if we evaluate this line at a 45-degree angle, we could do cosine 45 degrees and sine 45 degrees, and we will get 1 over square root of 2 and 1 over square root of 2, or square root of 2 over 2 if you want to move the square root to the numerator. And you'll see the same thing almost happen here, except when you insert cosine of 135, you will get negative 1 over square root of 2. Meanwhile, sine of 135 degrees is going to still give us 1 over square root of 2. So cosine x component and sine y component. When you do this enough with a lot of the common angles and such that you'll run into, usually these common angles are increased or decreased by a measure of pi or 90 degrees. This is the full standard unit circle. And essentially what you can do is that you can go, oh, hey, I'm calculating cosine of, let's say, pi thirds. And you can come here and you can go, oh, pi thirds is right here. And then you can look up at the x and y components, which correlate with this value. And you can very quickly go, oh, cosine of pi thirds gives me 1/2, or sine of pi thirds gives me square root of 3 over 2. And the same pattern goes on with the rest of the unit circle here. And that's essentially the unit circle in its entirety. We are now going to go through some examples using the unit circle. We're first going to begin with cosine. So as highlighted here, and kind of how I went through before, if you go down here and you're searching for through the angles, if you find 225, simply look at the x component of the point that this correlates with, and you'll get the value which you would get if you inputted this into a calculator. So cosine of 225 degrees is equivalent to negative square root of 2 over 2. Now, what about something that's a little bit more complicated? Let's say you had to find tangent at 45 degrees. Well, tangent really isn't represented here as we've constructed it. But in this case, you can actually use some of your geometric identities in order to figure out this value. And the identity that we're going to use is that tangent is equivalent to sine over cosine. When you insert tangent of 45, say here at the bottom, tangent of 45 degrees, that's going to be equivalent to sine over cosine of the same degrees. So then we can use this, look at our unit circle and go, oh hey, at 45 degrees, the x component is square root of 2 over 2, the y component is square root of 2 over 2. Therefore, we then plug those in and we get those same values divided by each other, and that gives us 1. And so pretty much anytime you run into tangent, it will be sine over cosine. And you can essentially use any series of geometric identities and boil it down to working with sine and cosine in order to get these tangible x and y values in there. All right, here are the sources. These 3 gave me all the things that I know. The last one I used for that unit circle, that full unit circle image. I hope this helped and you know a little bit more about how to use the unit circle. Thanks.